All right, thank you very much, everybody, for being here, and especially for the organization for allowing me to speak today about this project, ToroDB, and especially about scaling. This is a big data conference, and scaling is definitely a really important topic. So what we are presenting here is kind of funny thing. So ToroDB is a new database, a new NoSQL database. I'm going to give you a little bit overview of what it is. But also, we're going to be talking about how to scale SQL and how to scale NoSQL. It's very easy to scale NoSQL, right? It's probably not that easy to scale SQL. So this project that we are doing right now, which is, by the way, open source thing, allows us to scale SQL as if it were NoSQL. So the first thing that we're going to be showing today is that it's not certainly true that SQL does not scale. And so we're going to look at this from a complete perspective. So a little bit before starting about myself, as I've been greatly introduced, I'm Álvaro Hernández, worked for a company called 8K Data, and we focus on doing research and development in databases in general. So as part of that, we are creating products, software like ToroDB that we are talking about today. We also offer professional services, specifically in PostgreSQL, where we are very much specialized. And we're also the proud founders of PostgreSQL Spain, Postgres España, which has become one of the largest user groups, Postgres user groups in the world. Became the third largest one. It's now already the fifth, down to the fifth, let's say, with over 500 people in the group. It's pretty wild. So if you want to know my coordinates, you can see there my Twitter account, LinkedIn handle. So feel free to reach me back within the talk today or any time later on. So a brief description about ToroDB. Some of you may have been the year before here while I was presenting this technology when it was presented to the world. And today, I'm just going to make a quick introduction about the main principles of it. So in just one slide, ToroDB, it's a document-oriented NoSQL database. Not document-oriented, we're saying JSON, and it's a NoSQL database. It's open source, so this is not marketing talk. And what is very important is, first of all, it is compatible with the MongoDB protocol. So any tool that you can use from MongoDB, like drivers, GUI tools, command lines, program software written for MongoDB will work on ToroDB too. And what is really unique is that everything, all the data is stored on a database, on a relational database, on PostgreSQL. So ToroDB performs a transformation, a mapping, as we call it, from JSON documents to a relational database. And it's not just taking the whole document as a blob and storing it in a field, in a column, in a given table. That's a very naive approach. Somebody has taken that approach too. But the approach that we have taken, it's a completely relational mapping from the JSON document. So basically, as I was saying, the data is stored in tables. So we take a JSON document and split it in pieces, and all these pieces go to different different tables. The way we split documents is that if you take a whole JSON document and you look, there are some hierarchies, right? Well, we will take each of those hierarchies, each of those levels, and it will go to a different table. We call those subtypes, subdocuments. Now, when we look at the subdocuments, at the end of the day, they have a type. So if there's a person with name and surname and age, for example, the name and surname will probably be strings, the age will probably be a number. So there's a type there which is kind of a string number, sorry. So this is a type. With this type, we can infer a table and see to which table the data is going to belong to. Further on, we have a structure. A structure is a separate table which basically tells us for every document which shape it has. And this is going to be really important. You'll see how this relates to big data a lot. The structure, the shape of the document. This is stored on a separate table. Well, then simple stuff, the keys are mapped to attributes, to columns in the tables. And what is really important too is that the tables, everything's created automatically. There's no need to define a schema. So ToroDB is going to be creating tables for you all the time. You don't have to have any kind of intervention. Intervention is absolutely automatically. Let's see an example, so it's going to be easier to see. So imagine this document that we have here. So we have a document simulated with the name, data. Data contains a nested field, which is A and B. Then there's another nested document called nested. Sorry, it's not very original. And then it contains a J and a deeper, and within deeper, there's another document called A and B. So the first rule of what I was saying is that this document is going to be split into subdocuments, where each subdocument contains only one level of hierarchy. So basically, it's going to be split into these 4 levels. So we're going to have the first level, which has the name, the data, and nested. Name, data, and nested. There's the A and B. The A and B. Then there is J and deeper, which are belong to another level, J and deeper. And then finally, there's another A and B. Right? So we split the document into these 4 parts. Whenever there's a nested object, we have put here some curly braces, which basically means a pointer or a placeholder for the data that is nested within this structure. And these placeholders, we don't need to store them, because we're going to refer to them from an external structure. So basically, to store this data, we will need 3 different tables. The first one, which only contains the name, because the other ones are placeholders. Then 1 table for storing A and B, and then 1 table for storing the J. Notice that even with all we have here 4 subdocuments, we will need only 3 tables, because one of them, the table which contains the A and B, is going to be repeated, it's going to be reused, has the same type, which is basically a number and a string. And this is very important too. But let's see how it looks like in a real database. So once you run ToroDB and you insert some data, and this data comes into Postgres, it looks like exactly like this. So there's 2 internal fields called DID, document ID, and index. Don't need to worry about them yet. And the rest of the fields are the data we were inserting. Bear in mind that in MongoDB, there's always an internal field called _ID, which is a 12-character, 12-byte field, which is also represented here. So on table T_3, as you can see there, there's the ID and there's the name. And then there's table 1, which effectively stored those 2 subdocuments that I was showing before. And then there's table T2, which stores the J. About table repetition. So what we can see here is that we are reusing data structures. Tables in Postgres, as in any relational databases, are defined in a single place. Now, think about what means schemaless. Well, schemaless, there's no such thing. Data has always a schema. Otherwise, it would be really hard to query data later on, right? So if you just mix this name and the surname, how do you distinguish? There has to be a schema. The schema in schemaless databases, it's not less. It's probably attached. So the schema goes together with the data. Now, if you think about in a collection of millions of documents where there's just a few types of different documents, and by type I mean the shape, like the structure, how it looks like this document. Well, you're repeating all the time that schema that is attached to data, and that's metadata. So that creates a lot of repetition, and that turns out to occupy a lot of disk space, a lot of memory and cache, a lot of I/O. So a lot of performance. All right, let's go back to this. So we have the data. Now, how we pull this all back together. There's another table called structure. I hope you can read once in the back side. But it's basically a tiny JSON document telling us how to glue all these tables back together. So it basically says that the root level, it's stored on table 3. So if we go back to table number 3, we see that the table at the top is the root level. Then there is a field which is called data, which contains a nested document, which is going to be stored in table 1. Effectively, if we go back to table 1, we can see that there's the 42 hello world, which was the first, the data inside this data field. And then there's nested, which is represent table number 2, and then deeper, table number 1 with index 1. If we go back, we see the index here, we see that the 21 hello is the table number 1 with index 1, which was contained within deeper. So this basically represents and pulls back together the JSON document. And then we have a final table to create an association between the structures and the documents itself in a pure relational way. So we can reuse as much as possible the structure of the documents. And this is going to turn out into several advantages for us that we'll see. The first one is, I was saying, a very significant storage reduction. So to store the same data in ToroDB as compared to, for example, uncompressed MongoDB, like in MongoDB 2.6, there's a huge saving. ToroDB requires just down from 70% to 30% of the disk space required to store the same information in MongoDB in comparison. Now, why is this really important? It is really important because, first of all, we can also compress the data later on. So, we cannot compress this apples to MongoDB with compression, because this is free of compression. It's just avoiding to repeat all this metadata that is repeated effectively in many places. Second advantage is that saving disk space seems cheap these days, because disks are not very expensive. However, SSDs are more expensive. What we're saving here is I/O and memory in cache. So this is very significant, especially if you compare, for example, this with compressed data stores like MongoDB with WireTiger with compression enabled. Well, that is not compressed in memory. So there can be a very significant advantage here. So this is basically it about the introduction about the way ToroDB structures the information internally. As you can see, this is not a blob. This is just data split into tables in a hopefully smart way. What also comes out of this is something, as I was saying, very related to big data, to big queries. Is that what we're doing is effectively partitioning the data by type. Again, we call type the shape of the document. So we have a document with a name and a surname and an age. The type for us is name, string, surname, string, age, number. So we are partitioning the data by type because every different shape of the document, every different type goes to a different table. Now, what happens if you want to do a query and say, I want to query name and surname where age greater than 18? Well, of course, you cannot perform that query on documents which have not an age field. You cannot perform that query on documents which have an age field which is not a number, because they are nonsense. So what would happen on a typical NoSQL data store? If you need to answer those queries, and for whatever reason we will discuss later, you cannot use an index, what you need is a full database scan, which means that if you're running a 2 terabyte database, you'll be scanning a 2 terabyte database. Whereas in ToroDB will know that age needs to be present, needs to be a number, and we'll go to that structure table we saw before, and we'll say, oh, this can only be answered with data from table 16, or maybe 16 and 17. So go to those tables. Maybe those tables are just only 1% of the database. So rather than scanning 2 terabytes of database, you're going to be scanning 20 gigabytes, which is definitely less. 2 orders of magnitude less, or even less, of course. So running the types of queries that you will be running on transactional data stores, which are non-indexed, very typically, can see a huge, significant speed up in ToroDB just because we are partitioning automatically the data by type. We'll get a little back to this. But for now on, let's move on to the real topic in this presentation, which is scaling. And the way we present scaling here, it's that we wanted to scale a relational database as NoSQL scales. So first off, let's see, there's a big debate in the big data space. What is best, SQL or NoSQL? And just quoting some experts, like Ryan, basically Ryan is saying that SQL has earned the support for many users, for larger organizations, and it's just something you should have on your backpack, basically. So it's very well known, very established. So it's a probably a good tool from his opinion. However, if we look at a different opinion from Couchbase, basically they say that NoSQL is a viable alternative, preferable, especially when it comes to scalability. All right, so scalability. Let's talk about that. But what is a scalability? Because that's a nice word everybody likes to say, but what it really means. Because it might mean something different for different people. Like, you know, this is true, this is 2013, so 2 years ago. So don't take me wrong, but you know, MongoDB defined scalability to go beyond 100 gigabytes. That for a database, honestly, that's a piece of cake, or should be at least a piece of cake. You know, last week I was with a customer. They're growing a 13 terabyte database. That's single node. Yeah, that was Postgres. But anyway, you know, 100 gigabytes definitely not scalability. Now, what is really interesting about this post is that I completely agree with what they say there. Because when we say, let's scale, everybody goes to scale out and just new pizzas, new servers, and distribute the query and use sharding and everything. But that's tough. And it's definitely not free lunch, the horizontal scalability, on any NoSQL or SQL system. So maybe you should take some steps before scaling out for scaling. So let's look at the ways to scale. As I was saying, last week I was with a customer with a 13 terabyte database in a single node. That's definitely a matter of scale, and he was not scaling out. So let's look at, first of all, vertical scalability. This post was talking about, hey, let's go first vertical. So let's talk about vertical scalability. Let's talk about concurrency scalability, how you scale with concurrent operations. Let's talk about hardware scalability. How do you scale with better hardware, with more cores, which is, of course, you know, a tendency right now. Let's talk about query scalability. How fast are our queries? Can I distribute them in some way within the same node? Because we're talking yet about vertical scalability. And then let's jump into read scalability, or basically replication. And there's, of course, write scalability, horizontal sharding, which is probably a topic of a future talk. So vertical scalability. When we talk about concurrency scalability, if we analyze and jump into this debate between SQL and NoSQL, of course, always in my honest opinion, I think SQL does a better job, in general terms, of course. Like if we look, for example, at PostgreSQL, which I happen to know better than all the systems, it has a very fine-grained locking mechanism, definitely finer than many NoSQL databases. So that means you can do more things concurrently. Then there's also MVCC, the multi-version concurrency control, which basically allows you readers and writers to not interfere with each other. No locking required. So you can have write operations working at the same time as read operations. There's no locking involved, which means you get a way higher concurrency scalability. And there's usually better caching, because the caching algorithms in the, no pun intended, all databases, they've been developed for many years, and they are probably more advanced. So in terms of concurrency scalability, you usually get better results. And indeed, what is sometimes recommended on NoSQL is that if you cannot go further in terms of concurrency scalability, you better shard inside the same host. And this is a very typical configuration and deployment option. But again, as I'm going to demonstrate later on, sharding and replication, they are not free lunch. They come also with problems that we need to be aware of. So if you could scale inside the same host, vertical scaling in terms of concurrency scaling, better. Then there's, of course, hardware scalability, as I was saying before. How does a system scale with the number of cores? And what processor threading model it uses? There's definitely different results here, so I'm not going to discuss them, but it's something they should evaluate when you're evaluating a solution. And then query scalability. So you have a NoSQL system and a SQL system, you're performing a query. How is this query going? Is it able to use sufficiently the indexes? What type of indexes does the database has? Can you use more than one index? Because sometimes this is not the case in NoSQL stores, like most of the case in MongoDB. Can you do partitioning? Because partitioning in the relational world has a very precise meaning. And definitely, it gives you a lot of advantage in terms of scaling. But can you do partitioning on NoSQL data stores? Well, you can create different collections, but that's not the same thing. So you kind of need then to translate the responsibility to the application. So there's some definitely trade-offs. And then there's, of course, what I was referring to before, the query by type that we're doing in ToroDB. This is an automatic partitioning scheme, partitioning by type, as I was saying before. So this is something we have in ToroDB automatically. We're partitioning by type. So if you're doing queries restricted to subsets of the database, which is definitely the usual case, you'll benefit significantly for this automatic partitioning scheme that we call partition by type. So in terms of vertical scalability, I would say, in my opinion, that SQL relational databases do a better job. Let's look at replication, or read scalability. Well, if the idea basically is to replicate data to slave nodes, and these slave nodes are going to be read-only. So you can just perform read-only queries. Write to the master, scale out to the slaves, and perform read queries from the slaves. Both NoSQL and SQL support this technique. So there's different implementations with different flavors, but basically this is done for every database I basically know of. It turns out that binary replication, for obvious reasons, is usually faster, as is the case with PostgreSQL streaming replication, which has a replication lag extremely low compared with all the NoSQL systems, but it also has logical replication systems. But as I was saying before, it is really important to understand that even replication does not come without undesirable phenomena that can happen on the database. I'm pretty sure most of you, or some of you, have read this post. Can you raise hands who knows about this post, the Call Me Maybe series, the Jepsen series? Okay. Fewer than expected, unless you're just sleeping. Well, this post, I definitely recommend you to have a look at it. Look for Call Me Maybe, Jepsen, Mongo, whatever. But in summary, after a very deep analysis, what it says is two things. It's talking about MongoDB, so I'm going to talk about MongoDB a little bit. First of all, unless you use the majority right concern in a replica set, you're basically screwed up. Screwed up in terms of data safety. If you don't care about data safety, you're good to go. But if you care, you have to use replica majority. Nothing less than that will help you. And this is documented. The second takeaway, it's a little bit more subtle, but definitely not less important. It demonstrates that you can be facing two different kind of very undesirable events. The first one is called dirty reads. Basically, when a network partition happens on a system, there may be a time where there's going to be two primaries. It can happen that there's a network partition, a cluster divides into two groups. There's one primary here. There was the old primary, which has not yet realized there's been a partition. And there may be another primary elected on the other side of the partition. So there's a small window where there's going to be two primaries. So a dirty read means that a primary, which is on a minority, so even if we write with majority right concern, so this primary on the minority will not be able to talk to the majority and basically commit the information. So the client, the information that's sent to the client will be that the write has not yet been done. However, MongoDB very explicitly states in the documentation that when this write has been committed to the primary, but not, of course, replicated to majority, because there's no majority connected in that side of the partition, that data can be read by other slaves, by the clients. And then this primary steps down, and the clients have read data that it's going to disappear. So you're reading data that never should have been read. And this is called a dirty read. And this is a very difficult problem to solve. So if you're writing an application and you're using replication like this, you should be aware of this issue. And it's very serious. It can basically corrupt data in any possible manner. We can discuss whether this is more probable or less. I can tell you it's more than what you probably think. But anyway, you know, if you want to provide strong warranties about your software, like, you know, talking about finance, like in the previous talk, you shouldn't be able to run a consistent balance. You may get a balance that's not add to zero if you're faced with this kind of dirty reads. The other one is even more surprising. It's called stale reads. Stale reads basically means, again, imagine a partition and two primaries temporarily exist simultaneously. And a primary, which is in a minority partition, does not receive the update from the other primary, which is in the majority partition. And that write has been acknowledged and sent to all the slaves, so it's confirmed to the client. Now, the old primary still believes for a short period of time that it's the primary, and clients connected to it may do a query, will do a query for data, and the master will return the old data because it has not been able to receive the update. So it's returning an old value. And this is, even from the point of view of the documentation, should happen. But it's been demonstrated that it happens. By the way, the first issue, the dirty reads, it's supposed to be fixed on MongoDB 3.2, but I haven't tested it yet. So, just be aware of these facts that then can happen with replication. And finally, let's go to write scaling, multi-master setups, or sharding. Here, definitely NoSQL is doing a better job than SQL. But again, this is not neither full lunch. So there's some trade-offs in sharding. You probably are very well of those. Like, for example, there's no foreign keys. There's no way to reference data. And this is how you can scale out in writes, precisely because of this. That's why it's hard for SQL. It's not that people doing SQL are more stupid. It's harder because it's a more general case. Now, there are also solutions in the SQL space to allow horizontal scalability, like shared disk solutions like Oracle RAC. But of course, that's limited in terms of scaling, or PG shard in Postgres, or the Postgres foreign data wrappers, which is a way of connecting to external databases, and then you can use that to scale. But let's focus a little bit on read scalability, on replication, and how we've done MongoDB replication in ToroDB. So, as I was saying at the beginning, ToroDB, it's based on Postgres, so we write the data to PostgreSQL. And, well, Postgres has its own replication mechanism. It's going to be binary or logical, synchronous or asynchronous, whereas MongoDB has logical replication. Well, we decided to use the MongoDB replication protocol, even though it looks like an inferior protocol in terms of performance of replication, but superior in terms of features like master election and so on, even though it's not pretty good too, neither, but there's some support for that. We wanted to remain compatible with the MongoDB ecosystem. So we want ToroDB to be able to replicate from a real MongoDB and maybe replicate in cascade to another MongoDB node, so that it will remain indistinguishable from a perspective of MongoDB cluster and will behave as any other MongoDB slaves on the network. So let's look a little bit at how the MongoDB replication protocol works. So every change that happens to a MongoDB database, an insert, an upsert, of course, delete, an update, every change is recorded on a special collection in a format that is basically idempotent, which means that you can re-execute that change several times, the result will be the same. So if you say update I, which was 8, update I plus 1, the recorded change will be I equals 9 rather than plus 1. So if you say I equals 9 equals 9 equals 9, the result will not change. If you say plus 1 all the time, the result definitely will change. So this collection, all the changes that happen to MongoDB, they're automatically stored on a special collection called the local uplog RS collection. This is done by MongoDB automatically. There's some performance hit involved, but that's the way to scale out reads. So when it needs to replicate, the slaves are going to be pulling the information from this collection from the master node or the other slave node from which they are replicating from, and they basically pull this information. The changes are applied, and feedback is sent upstream. The slaves can be in 3 different states. So they can be on secondary state, which basically means they are following the differential information, that this change is happening to the database. They can be in initial sync, which is basically, let's copy everything to start a new replica. And there's the rollback. The rollback is a situation that can arise sometimes in which MongoDB needs to drop valid data. Like data was committed, but not replicated to the majority, and then a new leader is selected, which doesn't have that information. In order for me to follow it, I'll need to drop the data that is not common base, common denominator. So replication can also delete data. So how do we implement replication in ToroDB? So we first look at an implementation called MoSQL, which has been developed by Stripe, is open source too. And this is basically a very simple mechanism which connects to MongoDB and tails, with a tailable cursor, this collection, this oblog, and then applies it in PostgreSQL. But again, this is very simple. This is not implementing the replication protocol, cannot follow topology change, for example, it's not sending feedback, and so on. It just works, but it wasn't enough for us. So what we did, and I'm very proud to announce here today, is that we have just released a preview version of ToroDB 0.4, which enables, finally, replication from MongoDB to ToroDB. I'm sorry, but I want to ask you to please give a big applause to the team that has been doing this for several months. It's been a really, really hard job. Please come with me. Thank you. So this basically means that ToroDB, which again means Postgres, can now replicate almost real-time, synchronously, as any other MongoDB slave node, and get all the information that you have on MongoDB directly pulled to a database, a Postgres database. So no more need to ETL. If you're doing ETL some way, you no longer need. This is going to be a full slave in terms of participation in the replication protocol. So it implements a full replication protocol, as I was saying. And well, if you want to check the code, it's open source. It's on GitHub. Go to github/ToroDB, and you'll get there in the replication branch. If you go there and you like the code, please start it. We'd like to know that you liked it. So what are, at the end of the day, the advantages of scaling out using this type of replication in ToroDB? First of all, we have native SQL. This is very important. I'll come back later on to this topic. Then we have the query by type that I was referring before. So remember, we are partitioning by type automatically. You don't need to do anything else. And then when you do a query, it will target the subset of the database that can only be a positive result for that query. Nothing else. You won't be scanning the rest of the database. Plus, well, we have better SQL scaling. We mentioned that before. We have less concurrency contention. We also mentioned that before. We have better hardware utilization. That was also mentioned before. So we definitely improve here significantly. And there's, of course, no need to ETL. But let's even focus a little bit more on the native SQL, because most NoSQL now, and we've seen here this too, most NoSQL is now trying to get back to SQL, which is nice, because SQL has proven to be a really great tool for many people. But don't go, or better than going, with a NoSQL, a SQL-like interface, which implements a subset of the features available in SQL, which is pretty extensive. And sometimes maybe that it looks like SQL, but it's not SQL, which means that you cannot use it with regular SQL tools. Why not go with the native SQL layer? Because we have it here, it's Postgres. So you can insert with Mongo, and then query with SQL, which is in our opinion, a really good advantage. Plus, you get the really powerful SQL that comes with Postgres, which is one of the most advanced SQL implementations. We have like window functions, there's CTEs or common table expressions, which enables for recursive queries, there's hypothetical aggregates, there's many, many functionalities that will make your queries run sometimes orders of magnitude faster than with a more limited subset of SQL. And let me reinforce this even more. Please raise your hand if any of you is still using Windows 3.1. Oh, really? Okay, then you are the only one allowed here to use SQL 92. The rest of you, please abandon SQL 92 because it was presented at the same time as Windows 3.11. SQL 92 is select, where, group, by, join, having, which is what most NoSQL are trying to imitate, not even implement. PostgreSQL is hundreds of times more advanced than that, more powerful. If you want to know about it, there's a great presentation, it's shown here by a friend of mine, which talks about all the advanced features you can do in SQL. So don't stick to Windows 3.11. And finally, and also very, very happy to announce, to show you another feature, which we're gonna publish soon to ToroDB too, which is called ToroDB Views. So remember at the beginning that ToroDB basically takes a JSON document, splits into pieces in such a way that we can do query by type. But sometimes if you want to do SQL on top of those tables, it's definitely doable, don't get me wrong, but sometimes maybe a little bit hard. So wouldn't it be better if you could have a way of pulling back pieces of the documents in such a way that queries in a pure SQL way would be easier to do? So that's what we wanted to do, and this is how it works. So just imagine insert two documents in MongoDB, and then, or in ToroDB, they will end up being in tables in SQL. And then I use this ToroDB views. These are views that ToroDB is gonna create automatically for you. Again, there's nothing you have to do. And these views will take the name of the keys present here. So here you can say there's a person object, and there's a person.contact object nested within it. So ToroDB will create two views here. We'll create indeed three views, one for the root level, which is not depicted in the next slide, but then one view for the person, another view for the person.contact. And even if they were belonging to different tables, because if you look at these documents, like the person object has name and surname in the first example, but has name, surname, and age in the second example. In ToroDB, these two will go to different tables because they have different types, because one has an age field, the other one that hasn't. So they will end up being in physical different tables, but now this view unites them back into a single table, single view, which is called person. Age will be null, of course, for obvious reasons. The same happens with person.contact, as you can see on the bottom part of the slide. We're merging two documents where one of those doesn't have the Boolean field called verified. So this is something, it's unfortunately not pushed yet to GitHub. It will be pushed in the coming days. But it's another feature that we consider it's very interesting. Because what I'm trying to say here is that with ToroDB, you would be able to insert either directly on ToroDB, but using the MongoDB API, or from now on, in ToroDB, in MongoDB, sorry, on a master node in MongoDB, and then have the data streamed to ToroDB, and then query with SQL. So if you want to do big data, if you want to do reporting, if you want to use SQL for analyzing the data that it's on your transactional data store, you get huge benefits for doing so. And definitely, last but not least, one of the greatest advantages of doing this is that you can use the tools that exist nowadays to work with SQL. Because these SQL-like interfaces that are being developed right now for NoSQL databases are, again, SQL-like. But most of them, if not all of them, they are not pure SQL. And it's good that they look like SQL, because that makes programming easier. But as long as they're not SQL, they're not compatible with SQL tools. So you're basically left without tools. Whereas here, you can use any tool, like in the screenshot, the pgadmin interface, whatever you want to use. That will work because this is, again, this is underneath, this is Postgres, so this is a real SQL. So this is it. I guess we have some time for questions, if you have any question.
Oh, good. Yes, thanks. So let's have only one question because, sorry, we push you later in the schedule, but we run out of the 45 minutes. So just one question.
Okay.
Hi, I was wondering, when would you recommend actually using these NoSQL-like stores like Cassandra or React or that type of stores, given your experience?
You mean, when would I recommend those over?
Over SQL or ToroDB? That's not directly a competitor, but.
Okay, so I think they basically have different capabilities. So it depends a lot on your use case, what you're trying to achieve. Some of those offer better scalability. Some of those offer better data safety properties. Some of them offer native SQL, as we're offering in ToroDB. So I would say it's more of a matter of where your requirements are. There's no one size fits all. What I would say is that if you want to do SQL, if you can leverage the power of SQL, you have SQL tools, don't reinvent the wheel. So don't start building new tools, new services to either ETL from your NoSQL to a SQL data store to later on do the analysis with the tools you might be using, or just you want connectors. So don't write all that on your own, because I've seen many people doing that, many companies doing that. Just go for a solution like probably ToroDB, where you can just, it has a native SQL. So just realize this is the very first NoSQL database which has been built on top of a SQL database. And the good thing is that it exposes the good things that SQL databases have had. And it can scale, as was the topic of today, as a NoSQL. So you get basically the best of both worlds. So again, going back to the question, if you for whatever reason you appreciate SQL, or you have SQL tools, or you have SQL trained people, or you want to just perform queries faster for all the reasons that I have explained, I would say go with ToroDB. If you favor given NoSQL interface, API, or tools, or scalability, or whatever, well, you can go for other solutions. So it really depends on the requirements.
Thank you.
Thank you.
Awesome. Thank you very much, Álvaro.
Thank you. Thank you all.